Well, hi again, this is Bob, and we're getting ready to do a pretty short presentation here on, this is on page 445 at the bottom, and I'll pick it up where I left off because it gets a little wordy, but we're getting ready to discuss p-values for, excuse me, t calculations. And what I mean by that is that we have this formula, which we've just used in a couple of sample problems, and we know that there's two ways that we can deal with the results of that formula. One of them is we can look at the graph. Let's say we were dealing with a right-tailed test, and we had a critical value here. And if our t-value came out to be larger than that critical value on the right-tailed test, then of course we would reject the null hypotheses. Okay, well what we're doing now should seem familiar because we've done this once before with the z-tables. When we get our answer here, this time we're not, actually they don't draw the graph, although I usually recommend that we do draw the graph. But this time what we're going to do is we're going to take our calculated t-value and we're going to convert it into a p-value. Now you may recall that the p-value is the actual area in the tail. And it's the probability of getting a more extreme answer than we have now with regard to the null hypotheses. You can go back and review what we learned about the p-value in earlier section. I think it was 8.2. Recall also that the p-value is used sometimes instead of somebody will summarize the results of a study and they'll give maybe something like p or p-value equals 0.162. Okay, and I'll find it real quick because we just recently saw it on page 434. They give us some instructions on when to reject and when not to reject. And clearly a p-value of 0.162 is larger than 0.10, so we would not be rejecting. But if they gave us a p-value of, for example, 0.02, then we would most likely reject according to the rules that we saw earlier back on page 424. And you may recall if we get a p-value greater than 0.01 but less than 0.05, we reject the null hypotheses and we say the difference is significant. So anyway, if you need to refresh a little bit on p-value, you can go back on the top of page 434 to review the interpretation of the actual value. Anyway, what we're going to do, and it's very nice because all of our example problems can be gotten directly. We don't have to flip back to the back of the book to the table. They have an excerpt of the table on page 446, and we can just flip over to the next page. You're on that page. And so again, just remember that, again, I'll say we're talking about a right-tailed test. Let's say that we get a value after we converted our t calculation. That value, again, is the area inside that tail. In this case it is. Maybe the area would fall outside the tail, but that's the general idea. The p-value is an area, and that area can be changed into a probability, and we know that the probability has something to do with getting a more extreme answer in that direction, in this case the right tail. Anyway, let's back off the theory a little bit, and the only thing that's different between the P tables and the Z tables, and you'll discover this in just a second here, is that with the Z tables we can get an actual area, and when we're dealing with the T tables, we can't do that. We end up with an interval. Like, for example, we would get an interval maybe between our p-value is greater than 0.025 and less than 0.05. Okay, so we're going to get an interval in which it falls, but we can't get the area exactly. But having the interval will also allow us to reject or not reject the null hypotheses, as the case may be. But remember, when we were dealing with the Z tables, we could get the actual area. It was not expressed in terms of an interval. Some calculators will provide, or you can convert a t-value into the exact area, and some computers will do that also. But for our class, we're going to use the tables that are on 446. Anyway, let's do the first one there. You just did a t-test, and you ended up, and by the way, when I said you just did a t-test, I mean this. And when you use that formula, you ended up with 2.056. Okay, and your sample size was 11. So, of course, your degrees of freedom would be 10. So what we need to do, and you can now turn the page and look up to the, oh, I forgot to mention that the test is right-tailed. And of course, right tail is the same as saying a one-tail test. And you may recall that our tables are based on degrees of freedom, and then there's kind of a division here where we have the, on top, we have one tail, which we would use for the right or left tail type of a question. Since I'm a little out of room here, I'll write it this way. And then the bottom one is for two-tailed test. Those are the same as our alphas, okay? So if we were doing this question, remember our n was 11, so that means our degrees of freedom was 10. What we do is we run across that column horizontally until we find the numbers in which our t-value falls, 2.056. Our t was 2.056. Now, my graph isn't going to look anywhere as nice because they've actually got an excerpt of the table there. But if you notice, 2.056, even crudely on my graph, falls between 1.812 and 2.228. So it falls between there. So what we do, and remember this is a right-tailed test, which is like saying a one-tailed test, is we go straight up until that we get that one-tail column. And you're going to see two numbers here. Okay, actually those two numbers are alphas, or areas, and one of them is 0.05, and the other area is 0.025. Now, we don't know exactly what the how the exact area that this t-value converts to, but we do know this, which is almost as good. We know that our p-value, or actual area, is bigger than 0.025 and less than 0.05. So what does that mean? Well, it means that we would not reject at if we had an alpha of 1%, we would not reject the null hypotheses. But if we had originally set the alpha at 0.05%, we would reject because we know that our p-value lies between 0.025 and 0.05, and it's less than 0.05. So whatever that area is, we now know enough to reject because our alpha value our p-value is less than 0.05. But recall, we couldn't reject at 0.01 because our alpha value is bigger. When I say alpha value, I should say p-value is bigger than 0.025. Well, we can use this exact same excerpt to look at example 815. Just look directly above there. This time it's we've got a small sample size. Our t-test value is 2.983. And the sample size is 6. That, of course, means that our degrees of freedom is 5. And this test is two-tailed. So, of course, what you're going to do is I'll have to put this on the top of the next page here, crudely, of course, but it's good enough to show what's happening here. Here's our degrees of freedom. We're going to run down to 5. Here, let's say on this column would be our, I'll write it out this time, 1 tail, and then directly below is 2 tail. Okay, and we run across this way, and we find the two numbers between which our t-value of 2.983 fall. And when we do that, it falls between 2.571 and 3.365. So somewhere in between here, that value they gave us of 2.983 falls. So again, what we do is, don't forget this time we're dealing with two tails, is we go up to the two tail horizontal row there, and we find out the two values are 0.025, excuse me, I better look at this as carefully as I can here. 0.05 and 0.02. Right. So here's what we know. If we had the right computer, we could convert this 2.983 into a precise area. But since we are using the book's tables, and they tell us it's not practical to list out that number of degrees of freedom that table would entail, that we're going to use the interval. And in this case, our p-value would be less than 0.05 and greater than 0.02, meaning that if our original alpha was 0.05, we would reject the null hypotheses. But if our original alpha was 0.01, we would not reject the null hypotheses because our p-value is greater than 2. Okay, that's pretty much the idea of this. And let's do one last question that they give us here just to really hopefully solidify this. And they have the same instructions they did before, except after we, this is on the top of page 447. The only difference is after we get our t-value, we convert it to a p-value to make the determination as to whether or not to reject the null hypotheses. So if you notice, and I'm just so used to always drawing the graph or the bell curve and labeling it, but if you notice, they don't do this for this question. Okay, so I'm going to hope that we're understand what this would look like if I was putting everything on there for teaching purposes, but we really don't need to do that. What we need to first see is that we're asking if we're going to reject or not at 0.05. That means that we're going to use this formula And once we get a value for t, we're going to convert that value to a p-value, and then we're going to find out what two numbers it falls within. We can do that again by just looking at the top of the previous page, page 446, and then we're going to determine whether to reject or not. So anyway, they tell us that the doctor claims that the maximum volume oxygen uptake is greater than the average of all adults. This is for joggers. So right away we know the alternative hypotheses, and of course that would leave for the actual mean is 36.7. And of course we're talking about millimeters per kilogram. Remember, the doctor, this is a one-tailed test, the doctor believes that the mean is greater than 36.7 for oxygen uptake. Okay, and we've also got a sample size of 15 joggers. That immediately means our degrees of freedom is 1 less, or 14. That's the value, by the way, in case I haven't emphasized that we're going to enter the table with. And then finally, the sample standard deviation, S, is equal to 6 milligrams per kilogram. I'm just going to write 6 there. I'm not that familiar with jogging or the units. Anyway, the last piece of information we need, of course, got a small sample size, but they've told us that it's normally distributed, which means that we can use our sample standard deviation for our t-test. So this is what we would end up with. We would, oh, I forgot to write down the sample mean, 40.6. Okay, you know, sometimes I'm not familiar with the actual units, and I confess I don't do a lot of jogging, and I'm not aware of the units actually. But anyway, we would end up with 40.6 minus 36.7 divided by our sample standard deviation, which is 6, and then that gets divided by our sample size of root 15, and that turns out to give us 2.517. Now, prior to what we've learned about p-values, I just can't help from showing a little bit for instructional purpose. Okay, we don't know. We could find out, but to use the t-tables here or to interpret this answer, we don't know. Remember, this is a right-tailed test, and since we didn't find critical values ahead of time, we don't really know whether we're going to reject or not with a value of 2.517. Okay, so what they do, though, is remember that we were at alpha equaling 0.05. And so on a one-tailed test, so they're going to go to degrees of freedom, and they're going to divide this into one tail on top and 2 tails on the bottom. And we're going to run down to degrees of freedom, which you may recall was, where's that at here? 14 in this case. So I'm going to double check. Yeah, a random sample of 15 joggers, so our degrees of freedom, I should have written somewhere. Yeah, degrees of freedom 14. So what we're going to do to finish this question off is we're going to run down our degrees of freedom column till we get to 14. Then we're going to go across horizontally, and we're going to find 2 values between which 2.517 falls. Okay? And you can just refer right back over to page 446 on the top for that. For degrees of freedom 14, it would fall between 2.145, and I know my drawing isn't that good, but it's close enough to give us some help, and 2.624. Clearly, 2.517 falls between those values. So remember what we do then. For a one-tailed test, we'll go straight up, and we're going to find the values associated, in other words, the endpoints of our interval here. And it turns out that those values are, I just lost my place here. 14, I'm double checking because sometimes the book does make an error. It looks like it's 0.025 and 0.01. And you can verify that, of course. Greater than 0.025 and less than 0.01. I just want to make sure I didn't lose my place here. Okay, so we ended up, oh shoot, I did lose my place here. I apologize for that. I may have saw it, but I wrote it down wrong. For 14 degrees of freedom, we end up with one tail at 0.025 and 0.01. Okay. And I'll write that down quickly. Which I had right the first time, actually. You know what I keep doing, and I apologize for this, is sometimes when I get on the other side of the decimal, I mix up my, I'm so used to writing things as percents that I'll put them backwards. But now I'm sure that it's correct here. So I ask you to bear with me one more time. It's 2.5% and 1%, but as decimals sometimes I get them mixed up. Okay, so our p-value lies between 0.01, in other words, it's greater than 1% as an alpha, and it's less than 2.5% or 0.025 as alpha, and therefore since our original rejection or our original alpha test was 0.05, we would reject the null hypotheses. Okay, so I can't do anything other than apologize for the fact that I transposed the 0.01 to 0.025. Sometimes it is easier for me to change them into percents, but I'm sure that that will help with the idea of what's happening there, and also maybe remind us to be extra careful when we're interpreting our answers. Okay, I will be back shortly with section 8.4, which is something we've seen before also. It's this new material applied to the population proportion. Thank you.